In this module, we'll build the cryptography fundamentals behind Azure HSMs. You'll see how encryption, decryption, signing, and verification work, compare symmetric and asymmetric keys, follow a key's lifecycle, and identify common risks that can expose sensitive cloud workloads. You've already seen what an HSM is, where its trust boundary sits, and why it's used to lock down high-value keys in regulated environments. Now we'll zoom in on the cryptography those keys enable, how encryption works, what algorithms and key types exist, and how a key's lifecycle is managed from creation to destruction. Once those foundations are in place, we'll connect them to Azure security building blocks, and then to concrete Azure HSM services. Cryptography is what turns an ordinary cloud environment into a trustworthy one. It protects confidentiality so only authorized identities can see your data at rest and in transit. It preserves integrity, letting you detect any tampering. It enforces authenticity, proving who actually initiated a request. And it enables non-repudiation, giving you verifiable evidence of critical actions. Together, these properties allow Azure HSMs to securely run sensitive workloads at scale. Think of your data moving through three states. When it's stored in databases, disks, or backups, that's data at rest. You typically encrypt it with keys that are themselves protected in an HSM. When it travels over networks, it's data in transit. Protocols like TLS handle most of that protection. When applications are actively processing it, it's data in use. Here, HSMs protect the most sensitive operations like signing, decryption, and key generation. Symmetric cryptography is like having one powerful key that both locks and unlocks a vault. You use that same secret key to turn readable data into ciphertext and back again. The most common engine behind this is AES, which is everywhere in cloud systems, protecting disks, databases, and storage services. The big trade-off is key management. If that single key is stolen, every piece of encrypted data becomes readable. Asymmetric cryptography is all about key pairs that work together. You hand out your public key to anyone. They use it to encrypt data or verify your signatures. Your private key stays locked down, often inside an HSM, and is used to decrypt or to create those signatures. Algorithms like RSA and elliptic curve power this model, enabling TLS, certificates, workload identity, and secure key exchange across cloud environments. AES, RSA, and elliptic curve cryptography each play different roles. AES is the workhorse for fast, bulk data encryption, such as securing storage or VPN traffic. RSA and ECC are asymmetric tools, better suited for identity, digital signatures, certificates, and exchanging keys safely. In real systems, you usually combine them, choosing based on performance needs, compliance requirements, and platform support. Now separate two goals. Encryption is about secrecy. You take readable data, scramble it with a key, and only someone with the right key can turn it back into something meaningful. Signing is about trust. You use your private key to stamp data with a unique signature, and anyone with your public key can verify that stamp, proving who it came from and that it wasn't altered on the way. Hashing turns any input into a short, fixed-length digest, like a fingerprint of the data. If even one bit of the file changes, the fingerprint changes. So hashes are great for integrity checks. However, hashes alone don't prove who created the data. That's where HMAC comes in. It combines a hash with a secret key shared by sender and receiver, so they can verify both integrity and that the message came from someone who knows the key. When we talk about key strength, we're really talking about how hard it is for an attacker to guess or steal that key. Four things matter most: the secret key material itself, the length of the key for that algorithm, the quality of randomness used to generate it, and how well it's protected, ideally inside an HSM. Think of key lifecycle management as a controlled loop. We start by generating keys with strong algorithms and high-quality randomness. Keys are then activated only after approval, and every use is logged. Over time, we rotate keys to limit exposure and respond to new risks. Eventually, keys are retired, disabled, and securely destroyed, with backups handled under the same controls. Following this lifecycle keeps cryptography auditable, predictable, and resilient. Key onboarding is the front door to that lifecycle. First, decide exactly what the key is for. Encrypting data, signing tokens, or wrapping other keys. Then generate it only with approved libraries, managed services, or HSMs. Next, assign tightly scoped permissions so it can perform only those intended operations. Set an activation date so it's unusable until you're ready. Finally, enforce least privilege for every human and application that touches it. Keys have a life cycle, just like passwords. Rotation means regularly swapping an old key for a new one. Expiration sets a date when a key must stop being used. Revocation is a stronger signal. This key is no longer trusted at all. Disabling is a pause button, blocking use temporarily without deleting the key. Think of the key's later life as a set of guarded states. First, we create backups, so a hardware failure or cloud outage doesn't strand encrypted data. Restore is tightly controlled. Only approved admins in approved environments can bring a key back. Deletion removes it from daily use but keeps a safety net for recovery. Purge protection blocks rushed or malicious permanent deletion. Finally, destruction is deliberate, logged, and irreversible. You've seen how symmetric algorithms like AES protect data and how RSA and ECC handle key exchange, identity, and signing. You've also walked through the full key lifecycle and the risks of weak processes. Next, we'll plug these foundations into Azure identity, networking, policy, and HSM design.